Swayam Prabha. Digital India. Educated India.
So we'll quickly recap what we did yesterday, and then I'll continue with today's target. Okay, so today our target is mainly to capture certain important results in this direction. Okay, so how matrices help us, and especially the spectral properties, how does it help us to identify or describe the structure of the graph. Okay, sometimes without looking at the graph, how can we describe the graph itself? Just by looking at these numbers that we have in hand. Okay, so yesterday we saw about we started with the definition of eigenvalues, and then we entered into characteristic polynomial, and I also said something about minors and principal minors. This is in the linear algebra aspects that we had been seeing. Right, and with respect to adjacency matrix, we started looking at the connection between these two matrices, how it goes. So something more that I wanted to talk today about that results that we were talking is, so one was minors and principal minors, and we also saw how they are going to be connected with the characteristic polynomial, right. So any coefficient, so suppose I have determinant of A minus lambda I for any square matrix A, right, and suppose we write it as say B naught plus B1 and B1 lambda plus Bn minus 1 lambda power n minus 1 plus Bn lambda power n, and usually this Bn is going to be equal to 1 in our case, right. And so with this representation, we started talking about how these coefficients are connected to the minors, right. So one result that we can think about is, if we are talking about the coefficient minus 1 to the power of k into b n minus k, the n minus k coefficient, it is nothing but the sum of all principal minors of k, sum of all k by k principal minors, right, of order k, right. So this much we have seen already yesterday, so I am just quickly covering this part. So in this direction we also saw that our Bn minus 1 is going to be nothing but sum of all 1 by 1 principal minors, right. So what will be that? So if you look at this Bn minus 1, what is that? So I will have minus 1 into Bn minus 1, that is nothing but sum of all principal minors of order 1. What is the principal minor of order 1? All the diagonal entries, right. So it is nothing but, when we take sum of all the diagonal entries, it is nothing but trace of A, right. So if we also said that if we have the determinant has eigenvalues, say lambda 1 to lambda n, then we can also write the same polynomial as factors, right, lambda minus lambda 1 into lambda minus lambda 2 and so on. So with this representation, if we look at the power of lambda power n minus 1, we also know that this would be nothing but sum of all the eigenvalues, right. So this is all existing results. So these are all from linear algebra, we are just grabbing. So similarly, if you look at 2 by 2 principal minors, you are going to just take all possible combinations of 2 by 2 minors, and you will look at the sum of it, right. It is equivalent in our terms as product of, I mean all possible combinations of the product of two eigenvalues taken at a time, right. So this much we have seen. So now I just want to also talk something about spectral theorem, then we will enter into our graph properties. Okay. So, in spectral theorem, what does the spectral theorem say? I mean, it's a very huge theorem if you see in functional analysis or higher order linear algebra. If you see, it has all complicated results, but we will now restrict ourselves because we are going to only handle symmetric matrices, right. So, for symmetric matrices, what does the spectral theorem say? Given a matrix A, which is of say of order n by n symmetric matrix, we have so what can we say about the eigenvalues of symmetric matrix? So, the spectral theorem says that the eigenvalues of any real symmetric matrix, of course, we are also having, in fact, we will be having 0, 1 matrices, but for time being, let us consider only real matrices, right. So, given any real symmetric matrix, okay, the eigenvalues are going to be real, okay. So, it cannot have complex eigenvalues. So, that is one beauty of this thing. We are only talking about real symmetric, okay. We will not, we will go into the later part when we go into directed graphs, we obviously will not have symmetric matrices. So, in that case what will happen we will see later, but for our purpose we can see that the eigenvalues of A are real, okay, and excuse me, and there is also another interesting property that we would like to highlight here. So, for this matrix A, there exists an orthogonal matrix P. Say, what is an orthogonal matrix? Anybody remember? A inverse is equal to A transpose, yes, right. So, there exists a matrix P, okay, there exists an, in fact, we will say there exists an orthogonal matrix OM, I just mean for orthogonal matrix P, such that PA P transpose, as she said, orthogonal matrix as inverse is P transpose itself. So, PA P transpose is nothing but the diagonal, you get a diagonal matrix where the diagonal entries are the eigenvalues, right. So, this is your simplified version of spectral theorem. So, we will get back to this when we are looking at the eigenvectors, and when we need it we will pull out these results, but I am just giving you a priori, okay. So, and for some notations I will denote spectrum as spectrum of the matrix A, or in some books they also use this sigma of A, okay. And how do we represent this? There are two different ways of representing it. Suppose we have lambda 1, lambda 2 and so on with multiplicities, say m1, m2, m3, then we write the corresponding eigenvalues in increasing order, okay. Since we are talking about real eigenvalues, we can talk about ordering them also. So, we will arrange them in increasing order and we will represent it like how we represent a permutation, okay. Say suppose we have k distinct eigenvalues, then with multiplicity. So, by multiplicity what we mean, the occurrence of lambda I as an eigenvalue or a root of the characteristic polynomial is mi times, right. And this multiplicity is also called as the algebraic multiplicity. For an eigenvalue, if we talk about mi occurring m number of times, then we say that m is a algebraic multiplicity, or lambda occurs with algebraic multiplicity m, right. So, there is also another concept of geometric multiplicity. So, has anyone studied linear algebra like in detail, vector spaces, null spaces, except the scholars here? Okay. So, anyway, then in that case I will not go into it, but when we need it we will cross that bridge. So actually there is another concept of geometric multiplicity. So the geometric multiplicity is nothing but if you look at an eigenvalue and if you look at the eigenspace associated with it in a vector space, then the dimension of that space is nothing but the geometric multiplicity for that lambda I, right. So for time being we will skip that part, and it is also known that geometric multiplicity cannot exceed algebraic multiplicity. So it is always less than or equal to the algebraic multiplicity. So I will leave this part anyway because I have to touch other things if it is the case. Okay. So and in this direction we also saw something yesterday about the trace. Now also I started saying trace being equal to sum of the eigenvalues, and we also saw about the determinant of the matrix being equal to the product of the eigenvalues, right. So and one more thing what we will be concentrating on is the spectral radius. The spectral radius is nothing but the largest eigenvalue in absolute value, okay, in magnitude. Okay. So a spectral radius is just maximum over all lambda coming from my spectrum of A of mod lambda. So these quantities will help us as we go. We will try to characterize based on the spectral radius and other properties. Right. So coming back to our coefficient part, we talked about Bn minus 1, right. So now we will go into specifics of how these coefficients are going to be connected to our graph. Okay. So from now on, so all this is general results. So from now on we will talk about specifically for a given graph G. Okay. Given any graph G, we have now no more real matrix but only 0 1 matrices, right, 0 1 symmetric matrices. So we will restrict to that level, and from now on we will talk about only graphs. So given a graph G, so we know what is an adjacency matrix, right. What will be a, how will my 2 by 2 principal minor look like? We know, like if I am talking about a 1 by 1 principal minor, we know it is all diagonal elements, right. And in our case, if we are talking about simple undirected graphs, then we know it is all going to be 0, right. So from here what we have is in addition, we can also say that the trace of the matrix is obviously 0 because all our diagonal entries are 0 here. So how does that connect to our eigenvalues? We also know that we have trace to be equal to sum of all the eigenvalues, right. So for our graph, you can always see that the eigenvalues, the spectrum on the whole kill each other. You just take the sum of it, they will kill each other end of the day, okay. So by killing I just mean it goes to 0. Okay. So this is about 1 by 1 principal minor we have. So now next step, what about 2 by 2? How will my principal submatrix look in a 2 by 2 matrix? Say let us pick up an example, maybe that would help you more. Let me start with simple one, so it gives easy visualization at least. 3 here. Right. So what about 2 by 2 principal submatrices? So what are 2 by 2 simple submatrices here? Say suppose I take 1 2, I have to look at rows 1 2 intersection with the corresponding rows of columns of 1 2, right. So what will be that? 0 1 1 0, right. So if suppose I look at the first part, this is one principal submatrix. What about the vertices 2 and 4? If I look at 2 comma 4, so this is with the vertices 1 2. Say suppose I ask 2 comma 4. Take rows 2 and 4 and columns 2 and 4, right, and take the intersection of them. So that would be nothing but all 0 matrix, right. So if you look at the matrix and the 2 by 2 principal submatrices, you can see that if there is an edge in my graph, then only your 2 by 2 matrix will have a non-zero determinant. So next step is, once we have the submatrix, we need to look for a determinant of it, right. So we need minors, right. Next we will go for principal minors. So if you look at this, the principal minor is going to be nothing but -1, right. Determinant is -1, and for this we know it is 0, right. So a non-singular submatrix is achieved only if you have an edge between the two vertices that we are looking for in the principal submatrix. So what will happen to our coefficient, the corresponding coefficient Bn minus 2, these corresponding coefficients, it is nothing but sum of all 2 by 2 principal minors, right. So that means what? If a principal minor gives me value -1 if there is an edge between the corresponding vertices or the corresponding rows, right. If I take I comma j, then I will have a -1 as principal minor in that case, right. So if you take the sum of all these things, it is going to be nothing but so the sum of all the principal minors of order 2, right, 2 by 2 principal minors. I am just writing it roughly, okay. So this is not a notation, just to convey you. So this would be nothing but summation over all edges, right, because every other principal minus would become 0. I mean, if there is no edges, it becomes 0 and only edges are going to be accounted for. So this would be nothing but the number of edges. So actually there is a -1 determinant into number of edges, right. So -1 times we have number of edges. So this is what your 2 by 2 principal minor says. So if you look at the coefficient of lambda power n minus 2, that tells you the number of edges. So once you know these principles, it would become easy for you to even express the polynomial in an easy fashion in this way, right. So now extending this to a 3 by 3 principal minor, principal submatrix, when does the determinant not vanish for a 3 by 3 principal minor? So in this case, we can first let us look at 1 2 3 as a 3 by 3 principal submatrix, and then we will look at say 1 2 4, okay, 4 1 2, right. So if you look at 1 2 3, what is the principal submatrix? In this case 1 2 3, you have 0 1 1 0 0 1 1, right. This is the principal submatrix. So what is the determinant of this? -2, -1, 0, anybody else? 3, 4, 2, anybody else? Any other answer? +1, -1, okay, the answer is, so the determinant is going to be 2. I am writing it as like a matrix, but we are talking about determinant, right. So determinant of this matrix is 2. So now what about 1 2 4? So if I look at this triplet, what do we get? So 1 is 0 1 1, 2 is 1 0 0, 4 is 1 0 0, 0, right. You have, obviously it is quite immediate that you have repeated rows, determinant is going to be equal to 0 here, right. So what is the difference between these two? It is a cycle is adjacent or connected. So if you have, so in this 3 by 3 submatrices, we will be counting all possible triangles in the graph, okay. Every principal submatrix is going to give me a principal minor, non-zero principal minor, if I have a triangle formed by that vertices, right. So a principal, a 3 by 3 principal minor or sum of all this principal minors is going to give me, since determinant is 2, I should not leave that also, right. So it would be nothing but twice the number of triangles. So if you look at the coefficient Bn minus 3, it would give me all the entities in such a way that it is twice the number of triangles, right. So if we look at this sum of all the principal minors, then we get twice number of triangles in G, right. Okay. So I actually wanted to continue in this direction, but yesterday I jumped a little bit and I went into talking about distance between two matrices, right, distance between two vertices. There I made a mistake, I wanted to just correct it. So we were talking about two vertices if they are at distance m, right, and I also said that if we look at all the powers of A, we talked about powers of the matrices, and we said that a square until a power m are linearly independent, right. So, by linearly independent, what we mean is just you cannot write as a linear combination of any matrix here as a linear combination of the other matrices, okay. Over the real field, we can even think of it, we do not have to even worry about higher order, right. So, here the next result followed by this, what I wanted to say was, if we are given a graph G, okay, and we have k distinct eigenvalues, alright, then I also said that we have k to be greater than d. D is the diameter of the graph, right. So, here in the proof, when I was saying, I said something related to rank, but what I meant was, since we have at least m plus 1, say suppose if my diameter is d, then we will have at least d plus 1 linearly independent powers, right. So, a square and so on, a power d will be linearly independent, right. That means what, in my characteristic polynomial, I have a monic polynomial of degree d plus 1, at least degree d plus 1, okay. So, therefore, we will have at least d plus 1 distinct eigenvalues there, okay. By rank, what I meant was, I know since rank is at least d plus 1, there are non-zero eigenvalues, d plus 1 non-zero eigenvalues. There I just stepped a little bit and I said all the d plus 1 are going to be distinct eigenvalues because rank is d. So, I just want to correct that here, okay. So, if we have diameter d, then the result, next result states that if k is distinct eigenvalues of, I should not say k, if a matrix A has k distinct eigenvalues, now we are talking in terms of graphs, right. So, given a graph G, and if there are k distinct eigenvalues in the graph, then we can immediately say that this k is going to be greater than d, okay. So, the proof is very simple, that we have all these D linearly independent matrices, because we know if you go back to Cayley-Hamilton theorem, you know that every matrix satisfies its characteristic polynomial, right. So, from there also you can look into this connection, that these being linearly independent means what, your polynomial should have been monic polynomial for at least this d plus 1 power, right. So, therefore, we can immediately conclude that k is greater than d. So, I just wanted to make this small change over here, and before we ended up yesterday, we talked about some special classes that I wanted you to compute, say for Kn, right. So, what about Kn? We said it is Jn minus In, and we wanted to look for the eigenvalues, right, and we also saw that Jn has rank 1, it is only one linearly independent column is there, right. So, that means what? Rank 1 means there is only one non-zero eigenvalue. So, the remaining are all zeros. So, there are n minus 1 zeros as eigenvalues, and there is one eigenvalue which is going to be non-zero, right. So, what will be the value of that? For Jn, I am just asking for Jn. Just use the properties. We know trace should be equal to the sum of the diagonals, right. What is the trace for J? N, right. So, there is one eigenvalue of order sorry, which is equal to n, and 0 eigenvalues of multiplicity n minus 1, right. And we know for identity. So, if you look at Kn, so your Kn has a spectrum which is nothing but n minus 1. So, I said we will do in increasing order. So, let me stick to that. So, minus 1 is of order n minus 1. So, there are the repeated multiplicity of minus 1 is, or the multiplicity of the eigenvalue minus 1 is n minus 1, and there is an eigenvalue of n minus 1 with multiplicity 1. Okay, so, this is for the spectrum of Kn, right. So, can we say something quickly about this KPQ, complete bipartite graph? So, we will look at the matrix representation for this complete bipartite graph. So, how will my matrix look like? the adjacency matrix of complete bipartite graph. Say suppose I order the vertices so that the first one takes all the vertices from first partition, the first few rows, I arrange it like that. Okay. So, if we have such an ordering, then we will get a block matrix which looks like you will have, say, if for first p rows you will have a 0 and followed by all ones, which is going to be all ones matrix is going to be of dimension p cross q, and this side it would be q cross p, because we are talking about the second partition. So, from second partition you will have j q p, q cross p j matrix and a 0 matrix block, right. So, this is going to be the adjacency matrix. So, if I want to talk about the eigenvalue of this, so what is the rank of this matrix? So, we can quickly go through rank, it would be easier. Since we have block representation, we can easily see that rank of this matrix is going to be nothing but sum of the ranks of JPQ and JQP, right. So, rank of A is rank of JPQ plus rank of JQP. So, that means what? We know J matrix has rank 1, right, whatever dimension we are talking about. So, this is going to be equal to 2, right. So, so that means what? We are looking for 2 non-zero eigenvalues and the rest are all 0 eigenvalues, right. So, 0 occurs with multiplicity p plus q minus 2, right, total number of vertices minus 2. So, what would be these 2 non-zero eigenvalues? So, once again you can go through the principal submatrix idea. If you look into it, what do we know about the principal submatrix? With respect to eigenvalue, we know it is nothing but sum of product of 2 eigenvalues taken at a time, right. And what about the other side? Okay, before that I have to tell you one more thing. We have said there are 2 non-zero eigenvalues, right, and we also know trace is 0, right. So, that means what? If lambda is an eigenvalue, minus lambda will be the other one. So, again we can see that here there is a occurrence in pairs. So, lambda and minus lambda occurs together because of our easy property that trace is 0. Right. So, keeping that in mind, so we have 2 non-zero eigenvalues which is going to look like this, lambda and minus lambda. So, now to find out this lambda, we will resort to the second one, 2 by 2 principal submatrices. So, that would be nothing but the one side we know it is nothing but product of these 2, because the other eigenvalues are all 0. So, you can if you look at all pairing, I mean 2 at a time, if you pair only these 2 will exist, right. So, I will get minus lambda square if I take, and what would be the right hand side? Sum of all 2 by 2 principal minus sum of the edges, I mean it is the edges, number of edges, right, that we have already said. So, it is nothing but negative of E of g. So, putting this, how many edges are there? We are talking about complete bipartite graph with p vertices one side, q vertices other side, pq, right. So, lambda square is equal to pq implies lambda is plus or minus pq. So, these are the 2 eigenvalues, plus root pq and minus root pq, and they both occur with multiplicity 1. Okay. So, minus root pq is 1 and plus root pq is 1. So, this is going to be the spectrum, right, for complete bipartite graph. There is also another alternate way of doing this which we will see quickly. What about any bipartite graph? It is a generalization of complete bipartite graph, right, or I should say. So, again the structure is same for bipartite graph. You have a block matrix, so you have 0. The only difference is that you may not have the B matrix, J matrix, all ones matrix, because it was complete we had all ones, that was one easy way of looking at it, but we will not have all ones possible here. So, we will have a B matrix, something which takes the adjacency into account, and this side we will have B transpose, the transpose of it here followed by 0. Okay. So, this will be the structure of the adjacency matrix. In fact, even for incidence matrix a similar structure will be there. Okay. And So, if suppose I want to find the eigenvalues, the same principle will go. So, we can have at the max 2 non-zero eigenvalues. If there is at least one edge, then we should have rank at least 1 on either side. So, we can see that rank is going to be 2 for this matrix also, and by the same argument as before, you can easily see that your lambda square will be equal to, is it PQ? So, he asked this question, rank will it be 2? So, anybody else has an objection? I have put forth a statement. I want to ask you, I have just generalized it from a complete graph, then why do we have, I mean, what will be the difference between complete graph and other graphs? Okay, I want to just take your attention, it need not be 2, okay, that is what I was just putting it forth to you, rank is 2 just to test you, okay. So, rank need not be 2 here, but whatever is the rank, it is going to be even, okay, because as we will see now, we can see that if lambda is an eigenvalue, then minus lambda will also be an eigenvalue, okay. So, so suppose, so let me go into this proof part. Say suppose lambda is an eigenvalue, and say we have an vector, eigenvector, say let me just write it as xy, where x is of order say p and y is of order q, okay. So, my total, I have my vector xy, so x corresponds to the first block kind of thing, okay. So, if I write it this way, then what can I see? What can I say from here? Say I have this matrix 0b b transpose 0 into xy, this would be equal to lambda times xy, right. So, by my representation, if lambda is an eigenvalue, this should be true, right. Excuse me. So, what can we say about this? So, from here say I can just keep this as like I have by is lambda x and b transpose x going to be equal to lambda y. So, let us keep this in mind.